In the last two lectures, we've seen that we've looked at two special cases, two examples, one where a bunch of gas molecules expand to fill up a box, and a second where a chemical reaction takes place, and where the formation of the bond releases a bunch of energy into the surroundings. So in the first case, matter is spreading out, and in the second case, energy is spreading out. And in both cases, the number of microstates available to the system plus the number of microstates available overall to both system and surroundings increases, and therefore the entropy increases, and therefore the statistics drive a spontaneous process, a spontaneous, irreversible process. But that's all very abstract. That's pictures on an iPad, as the case may be here. Let's look at some more complex or more realistic examples. There's still just going to be drawings down here, but at least a little bit more realistic examples of how this looks when we're talking about real systems. Let me say that at this point, so far we've talked at least pretty much exclusively about what's called translational entropy. That means an increase in the number of microstates available to the system due to the fact that molecules can move around in space. Those are called translations. And so it's translational entropy. Moving the molecule around is a translation. When you can move it around in a bigger region, then there's more translational microstates, and therefore a rise in translational entropy. But there are other kinds of entropy as well, and we'll look at some of those kinds in just a minute. All right, so in the first case here, here's our particles expanding to fill a box. But let's suppose instead of the box being just vacuum, it was filled already with water, and the particles, instead of just being gas molecules, are sodium and chloride ions dissolved in the water. And there's a barrier in place to begin with, but we remove that barrier. We know what will happen. The sodium and chloride ions will spread out to fill the box. The pure water that was over on this side will gain a certain concentration of sodium and chloride ions. Everything will spread out. W will increase, and it will increase for exactly the same reasons as it increased in the case of the gas molecules. The translational entropy will increase. Likewise, if I have a molecule like this one, where there are two parts to it, A and B, but it's bound together in a single unit that can run around inside the box freely enough, but it always has to stay together, and then we break that bond or tear the molecules apart somehow so that they can now run around independently, then W for the system, at least, will increase, right? We may have had to put some energy in from the surroundings to do that. That was the example, case 2, that we talked about over here, for example, last time. But as far as the system alone is concerned, the number of microstates increased, and therefore the entropy of the system alone increased. Here's an example from a much more realistic example from biology. We saw this as a movie, as a video, in the very first class period, where you have a whole bunch of hydrogen ions over here, a high concentration of hydrogen ions over here, a low concentration of ions over here. The ions can travel from one side to the other, but they have to do it in this constrained way, right? They have to go around this spinning lower cylinder that is driving the upper cylinder, or rotations of the axis, and therefore driving deformations of the upper cylinder. And now we see why that's a power source, or an energy source, or what's called Gibbs free energy source. When the H+ ions on one side travel to the other side, they're increasing the number of microstates available to the H+, and therefore increasing the entropy, and therefore that will happen spontaneously, and that will happen spontaneously even if they have to go through this complicated process of traveling around the barrier and out through the little port on the other side in order to do it. Statistically, they'll do it slower, and it will take some complications for them to get from one side to the other, but statistically it will still happen. It will happen with a certain rate depending on how much difficulty there is in traversing the membrane. And that means that other sources of thermodynamic free energy can pick up the energy that's released when the protons travel from one side to the other. And in the case of this particular molecular machine, it's designed and arranged in such a way that that energy that's released gets recaptured now as ATP molecules. It gets used basically to put together spent or burnt ADP molecules plus PI plus inorganic phosphate to form new ATP, new live ATP molecules. And the same thing happens, of course, in a more passive way for every ion channel in a cell membrane or a cell wall. If you've got sodium, for example, on the inside in high concentration and sodium on the outside in low concentration, then the total entropy or the total number of microstates available to the system will increase when sodiums go from the high side to the low side, and therefore they will do that spontaneously. They'll flow through and they'll continue doing that until, if it's possible to do that, the concentrations on both sides are equal. And what will happen then? Well, then things will still continue to flow statistically. They'll just flow with equal rates in both directions, so there won't be any net flow of ions from one side to the other. Things really never stop moving, of course. There's always randomness, thermal energy. But if there's a concentration difference, then the rate of flow from the high to the low side will be greater than the backflow. Here's a little less obvious example of the same kind of thing where translational entropy is driving things. Here I've got an ethanol molecule. The ethanol has a polar end, right, an OH group at one end. And the water molecules are attracted to that polar end, right? It's a hydrophilic end of the molecule. The water molecules are attracted. That means that statistically these water molecules are partially bound to that end of the molecule. They're more likely to be here than they are out in the bulk, even if they're not, stuck hard. They come on and off and so on, but they're still more likely to be close than they are to be far away. Now this ethanol molecule gets bound to a protein. Say there's a binding site on a protein for ethanol. And inside the binding pocket of that protein, there's no space for the water molecules. And so in order for that binding to take place, the water molecules have to be released, and statistically released, that is. And that means that these water molecules now have more freedom than they did before. Obviously, a lot of other things are happening at the same time when this binding process takes place. But at least as far as the waters of hydration are concerned, there's a net gain in entropy because of the release of the water molecules, even though there's a net loss of entropy, for example, because of the binding between the protein and the ethanol molecule itself, and there may be other processes that are going on as well. All right, that's all translational entropy. But suppose I have, for example, a single water molecule. Water molecules have a dipole, which means that if I apply a strong electric field, I can align that dipole. That means that the rotations of this water molecule, you can never really get them to zero, but they'll be restricted, right? This water molecule's rotations are less free than they would be if the field weren't on. So that means that if I turn the field off, we expect that the number of microstates available to the system will increase, right? The translational microstates, the movement of this whole molecule as a unit, hasn't changed. It was free already and it's still free over here. But the rotational degrees of freedom, the angles that are available to the system, have increased in going from the field on to the field off. And so there's rotational microstates, and therefore rotational entropy as well, and this represents an entropy increase. There's lots of effect. Water molecules are extremely important, of course, in biology. Water is an extremely important thing in biology, and there's lots of effects. We'll talk about the hydrophobic effect, for example, which is largely a result of exactly this kind of thing, but we'll come to that later. If I have a molecule like ethane here that has a single bond in the middle of it, and let's suppose somehow, I don't know right now how exactly that would be done, but let's suppose I lock that single bond. I guess I could make it a double bond partially somehow. Anyway, let's suppose I lock it. Then there's a degree of freedom, the rotation about that double bond, that is restricted. And if I then unlock it, this end of the molecule can spin freely relative to this end of the molecule, and therefore I have an extra degree of freedom, or the range of one of the degrees of freedom in the molecule has increased. Therefore, W is increased. Therefore, entropy is increased. That's called, well, I was going to say rotational freedom, internal rotational freedom, internal rotational entropy. Here's a more dramatic example of that. Let's suppose I have a short peptide chain like, well, I've drawn schematically here, and it's bound to the surface of a protein to begin with, and it's bound in such a way that it's specifically stuck at all the locations here. So there's interactions here that are sticking it. And that means that all these angles between the units along the chain are also very restricted. Of course, you never restrict anything to zero. There's a little bit of fluctuation of the angles here, but they're largely locked. Now you take this molecule off, and it's free to move in solution. Well, now all those angles are free, and there is a rather large, depends on the size of the molecule, but there can be a fairly large change or increase in what's called chain configurational entropy. That configurational entropy is, again, that increase is due to an unlocking of a degree of freedom, a bunch of degrees of freedom in this case, right? Not just one. All these angles become free, and therefore an increase in W, and therefore an increase in entropy. Here's a place, an experiment that has become kind of commonplace now, but was brand new back when I was a graduate student, back when I was a postdoc anyway, that illustrates this idea exactly, and also illustrates a couple of new ideas that I think are nice to see. It's called a laser tweezers DNA stretching experiment. So you have a DNA molecule here. It's attached at one end to something rigid. Usually it's another bead, but it doesn't matter what it is. And then there's a plastic bead attached to the other end of the molecule, and that plastic bead, it turns out, can be picked up, can be grabbed by something called a laser tweezers apparatus. Basically, that's just a focused light. So you put the thing in a microscope, you shine light through the microscope lens, laser, in fact, through the microscope lens. That makes a really intense laser light region right here. And it turns out that plastic beads are attracted to that region. And that means that you can pull with the bead. Now that you've got the bead in your trap, you can move the trap, and you can pull the bead, and therefore you can stretch the DNA molecule. When you do that, look what happens to the angles of the DNA molecule. When it's down here, the DNA molecule is basically free. It can change its shape pretty much at will. There's most of the chain configurational entropy of the DNA molecule is still present when you're at short extension like this, but when you pull it out long, these units in the DNA are now much less free. I mean, they're not locked completely, right, but every one of these little angles is now much less free, and there's thousands of them now. It's a long piece of DNA. Every one of those degrees of freedom is now less free, is more restricted than it was before. And so entropy has actually gone down and gone down dramatically as you're pulling. And the way that manifests itself physically is that the DNA molecule starts resisting the ability of the laser tweezers or the laser trap to pull the DNA any further, and at some point the force you can exert with the laser trap isn't strong enough anymore to continue stretching the DNA. The two forces, one produced by the DNA and the other produced by the laser trap, become balanced, and the system stops. The stretching experiment stops. You can plot how much force the DNA is exerting on your trap, is resisting your trap, versus the length or distance that you stretch things out. X is how far is the distance between the ground here and the position of the trap. So as you increase the distance, as you're pulling things out, you can measure how much force the DNA is generating, and it turns out it doesn't quite go to infinity, and all kinds of funny things happen up here, in fact, but it goes very high. And this effect, especially for the shorter extensions, is a purely entropic effect. It's purely due to the loss of chain configurational entropy due to straightening out the chain and therefore restricting the angles that are available to the links in the chain. If you could, for an ideal case, if this piece of DNA were non-stretchable and ideal in other ways, then you can show mathematically that as you pull and stretch the chain and extend the chain further and further, the chain entropy approaches zero, and the force, the countervailing force that the DNA produces, approaches infinity. And that's what I've shown in this graph here. And so, lessons from this case. Entropy can generate physical forces. In the earlier cases that I showed up above, it wasn't obvious, at least. I mean, things happen spontaneously, and I guess you can call that quote-unquote a force. But down here with the DNA case, it's actually a physical force. If you grab this bead with your fingers, you would feel it pulling back against you. So entropy, purely a statistical thing, can still generate a physical force. And furthermore, that force can, in principle, at least ideally, it can go to infinity, which means that entropic forces aren't weak, ghostly things. They can be very strong. And in fact, we'll see many examples of very strong, essentially entropic forces and energies and so on as we go through the semester. All right.